Hi, it's Mr. Anderson, and this is Environmental Science Video 12. It's on population ecology. One of the greatest conservation stories in biology is the story of the whooping crane. They used to number 10,000 in the US, but by 1938 their numbers had dropped to only 15 individuals. So scientists had to figure out where are they breeding, how do we protect those areas, and you can see the population is starting to rebound. But the health of the population is dependent upon the size of the population. How do we increase the size of a population? Through births and immigration, new individuals coming into the population. Likewise, how do we decrease it? Through deaths and emigration. These things contribute to what's called the intrinsic growth rate. Is it increasing or is it decreasing? It's not the only characteristic. We also have the density and distribution. We have the sex ratio and the age structure as well. But what other factors outside of this intrinsic growth rate can affect their growth? Well, we break that into two groups, density dependent and independent. Density dependent factors are factors that limit growth based on the density of the population. So if you think about it, as the population's density increases, if there's not enough food or water or shelter, we call those limiting resources. And what happens to the population? It'll eventually level off. It hits something called a carrying capacity, or K. It's the maximum number of individuals an area can support. We also have density independent, and those are going to be things just related to chance. So a flood or a fire could be examples that limit the size of the population. So in population ecology, we're studying these factors, and scientists come up with models that help to describe what's going on in a population. So a famous model is the exponential growth model. What we're looking at is this growth rate and how it's increasing the population over time. And then we have a logistic model. It's also showing exponential growth, but eventually it's reaching what's called a carrying capacity, or this limit of population growth. Scientists also study strategies that species have. Some are what are called K-selected. That means their population size will increase until it gradually hits a carrying capacity, and those who live more of a boom or bust cycle that are R-selected. And we can look at how long individuals survive, and that tells us a little bit about which strategy they're using. And so the population size is incredibly important. So if we have these rabbits, so we have 9 rabbits, then their N value at this point would be 9. If we lose 2 of them, our N value is 7. If we gain 3, now our N value is going to be 10. It's the set number we have. But also density is important. That's the number of individuals we have in a given area. And so we could call this one density, but we would call this greater density. We could also look at their distribution. I would say that these rabbits are now randomly distributed, but they could be distributed uniformly, or they could just be clumped in their distribution. And we could also look at their sex ratio. So how many of our males and how many of them are going to be females. And we could expand that to look at what's called their age structure. Not only what is their gender, but also how old are they. So we could organize them like this, where this is going to be our first year female rabbit, second year, and third year, and we can do the same thing with males. But when it comes to the health, the population size is incredibly important. It's dictated by births, deaths, immigration, and emigration. And so we have a formula that allows us to look at that. And the calculations are very simple. You can do them just in your head. And so let's say we have a population of 10. So our N naught is going to be 10. That's our initial population. Here's our equation. So it's really simple. The change in N is going to be the births minus the deaths plus the immigration minus the emigration. So let's look at this population over here and see what happens. So this rabbit gave birth to 3 other rabbits. And so if we write this out, what's our births going to be? It's going to be 3. Now let's watch the population again. So you can see one of the rabbits died. And so we're going to put a 1 here in the deaths. We could look at immigration. How many come in? Looks like just 1. So we would put a 1 right here. And then how many emigrate? It looks like 2 left, and so we would put a 2 right here. And so the delta N, or the change in N, is simply going to be 3 minus 1 plus 1 minus 2, or 1. That's the change, or we've seen an increase in 1. Now what's the growth rate? The growth rate is going to be the change divided by the initial population. So 1 divided by 10 gives us a 10% growth rate, or 0.1 is our growth rate. We call that the intrinsic growth rate. And as long as we have no other factors outside that population, that will remain constant over time. And you could solve a really hard problem. If we have 1 million people in an area, 100,000 are born, 10,000 die, if you're given the immigration and emigration, you should be able to calculate R for that population. So if we study a group of rabbits over time, their population will increase, but it'll eventually level out at some point. Now that leveling out point is called the carrying capacity, or the K. Now why is a population going to level out? It's because they're running out of something. They're running out of food or water or shelter. And so we all call all of those things limiting resources. Disease could be another limiting resource. The more rabbits we have, the more disease, and so it's eventually going to level it off. Now it won't look perfect like that. In a normal population, it's going to have overshoots and it's going to have a lot of die-off, but we're going to have that average that we eventually hit. These are density dependent factors because they're based on the density of the population. We can also have density independent. So imagine that these rabbits over on this side are killed in a forest fire. That's just chance. It's just chance taking over, and so it's not based on the density of rabbits that we had. So if we start to use models to explain how this works, a really important model is the exponential growth model. And so the equation looks like this. It's a little scary, but it's really not that bad. N sub t is going to be the population at any time into the future. N sub O is going to be the initial population. So let's say we start with a population of 10. R is going to be the growth rate. That's that intrinsic growth rate. And T is going to be time. So the only thing that you really don't know in this equation is E. E is going to be E, the mathematical constant. So it's a number. It's just like pi. It's going to be 2.718. It just keeps going like that. So for our purposes, we just think of it as 2.71. And so let's say we want to figure out what's going to happen to the population in year 1. So if we want to figure out, we started at 10, what's going to be the population probably at year 1, we just use this equation. So E is going to be the same. So what's going to be our R value? Our R value will always be 0.5. That's that intrinsic growth rate. What's our T value? Our T value is going to be time. What's our initial population? It's going to be 10. So if I expand that a little bit, we're simply multiplying 1 times 0.5, 1 year times that growth rate. And so that's going to be 10 times 2.71, again, that's E raised to the 0.5 power. So that's really like taking the square root of 2.71, and so that's 1.64. So if we work that out, that's going to be around 16 rabbits after 1 year. So let me graph that, and let's go to year 2. So same thing. We're going to plug in our value of 0.5, but now our T value is going to be 2. Still have that same initial population, and so now it's going to be 2.71 raised to the 1 power. So what's that? That's simply 2.71. So if we work this out, now we're going to have 27 rabbits in that next year. You can see the population is increasing. We're starting to see that exponential growth. Let's go for year 3. So if we figure out year 3, again, our intrinsic growth rate is still 0.5. 3 is going to be the year we're at. Still have that same initial. And so this is going to be 2.71 raised to the 1.5 power. You'd probably need a calculator to do this. We now get 44.6, or let's say 45 rabbits. So if we graph it, you can see that the population is increasing like that. We have what's called a J-shaped curve, and it's going to increase rapidly over time. The whole world would be filled with rabbits if we keep following this model. And so we know that's not what occurs. And so not only intrinsic growth rate is important, but K, that carrying capacity. So if you're given a problem like this, could you graph what's going to happen over time? If K is 70, well, you're going to get something that looks like this. It's going to be J for a while, but it's eventually going to curve off, and we're going to have an S-shaped curve. This is a logistic growth model. There's also a mathematical model we won't work through. I'll put a link to another video where I do that down below. And so scientists, now that they have models, they can start to apply that to nature. So what we found is that species kind of fall into one of two camps. We have what are called K-selected species. Those are going to be species that their population increases, and then it'll eventually hit a carrying capacity and it stays there. What are some characteristics of species like that? They're going to give a lot of parental care to their offspring. They're just going to have a few offspring. And so the whooping crane would be an example of that. Humans are an example of that. We don't just go up and down in our population. R-selected are going to do that. So an Arctic hare is an example of that. A famous study was looking at the pelts that were collected by the Hudson Bay Company, and they found from 1850 to 1930 that the population of Arctic hare just went up and down and up and down. And so hares are going to be groups of individuals that have lots of offspring, they don't get tons of parental care, and their population is going to increase, and then it'll crash. So we have this boom and bust cycle. Now what's interesting is that there's another species, and so the Arctic hare are fed on by the Canada lynx. And if we look at their population goes through a boom and bust as well. We have what's called a predator-prey relationship, where as the Arctic hare population increases, then we can have more lynx feeding on it. But as they crash, then the lynx are going to crash as well. Now, a way to look at which strategy species are using is figuring out their survivorship. And so we have time on the bottom, and then we have the survivors on the side. So if we look at humans as a type 1 survivorship curve, what that means is when we're born, almost all of the humans survive. And then throughout their lifetime, they all die right at the end. And so we give a lot of parental care to our offspring, almost all of them survive, and then when we get into our 80s, 90s, then we all die off. We could also have a type 2 survivorship curve. Songbirds are an example of that. From the moment they're born, they're dying off at a constant rate. Or we could look at type 3. Those are individuals like the acorns from a tree. Almost all of them die, but a few of those survive, and those make up the plants that we have. And so could you link that to K or R selected species? Well, type 1 individuals are generally going to be those K selected species, and then type 3 are generally going to be those R selected species. But there are so many examples that are in the middle. So if you think about a sea turtle, for example, they have lots of offspring. They don't give much parental care, but they live a long time. And so it's not as simple as are you R or are you K? It's somewhere in the middle, but they are applying these different strategies in life. And so did you learn the following? Could you pause the video at this point and fill in the blanks? If not, population size is determined by immigration and birth, that increases it, decreased by emigration and deaths. We've got other characteristics: density, distribution, sex ratio, and age structure. There are density independent and dependent factors. Density independent, remember, are related to chance. Density dependent lead to what's called a carrying capacity, or K. We use models to study it. Exponential models are built on the growth rate. Logistic models also built on the growth rate but include carrying capacity. And then we have different strategies in species. K selected, R selected. Remember, we're K selected. And then we have survivorship curves that we can study to get that. That's a lot. I hope it made sense, and I hope that was helpful.